Hi Kidlets, these are your second to last set of notes for the moon. Today we're talking about eclipses. So here are some definitions that you need to have for eclipses. These have to do with the orbital geometry, and we will be dealing with these for the rest of the year as well, because during the next unit we're going to be focusing on orbits and the mechanics of orbits. So eclipses are a consequence of the sun, moon, earth geometry and the places that the moon is in within its orbit. And even within the different moon phases, we have these different orbital positions that are a consequence of the moon having an elliptical orbit as opposed to a circular. So if we think about a circular orbit being like that, an elliptical orbit is like this. And it's only slightly elliptical. So perigee is the place that is closest in orbit to a larger body. So if we think about the Earth as being right about here, so it's slightly offset. So perigee would be this position here. So then apogee, when you put an A in front of it, means opposite. So apogee would be this position over here. So just a review, the ecliptic is the apparent path of the sun on the celestial sphere. So that's what we consider to be like the center of all of our orbital positions in the solar system. And then the nodes are the alignment of an orbit with the ecliptic. And we can only have an eclipse when that body is on the ecliptic on a node. So that would be where it slightly crosses. Because we don't have eclipses every month because the orbit of the moon is slightly off. It is 5 degrees off from the orbit of the Earth. So if here is the orbit of the Earth, the orbit of the moon is like that. So we can only have nodes, or we can only have eclipses when it's on the node like that. So our first type of eclipse, and we've already seen both of these this year, as a lunar eclipse. This should be a bit of a review for you. So when the Earth is between the moon and the sun, so the umbra is that total shadow. The total eclipse is when it's within the umbral shadow, and the penumbra is the partial shadow. And as we've already seen, we see that red, and here is that period. So the shadow of the Earth is much larger than the moon, so we see it in complete total eclipse when it's passing within that. Alex made that beautiful time lapse showing this. So again, just as a review, any light source actually has an umbra and a penumbra. It's not restricted to just the Earth-Moon system. So any light source will have a portion of complete shadow and a portion of diluted shadow. So lunar eclipses again. So again, like we said, the orbit is slightly off. So it's only when it's on those nodes that we can have an eclipse. But it's a lot easier, it's much more favorable to have a lunar eclipse than a solar eclipse because the shadow of the Earth is so much larger. So here would be the umbra again, and then we have a much larger zone of the penumbra. So here that is one more time. So here would be what we would see. So this is the motion of the moon against the background stars. So we can see as the moon moves into the umbral shadow, it gets reddened as it scatters the light from the atmosphere. So you guys all got the opportunity to see this earlier in the semester. Lunar eclipses can last a long time, and we see this red moon because of the atmospheric effect. It doesn't mean that the moon actually changes color. This is purely optical. If you're on the moon, you wouldn't see that. So here is a table showing the total and partial eclipses of the moon. So this is just for lunar eclipses, not for solar, except that when we have a lunar eclipse, that generally means we're going to have a solar eclipse in the same month. So this is based on Greenwich Mean Time, so not PST or CST. It gives you a little table of how to read that here. If you experienced complete totality, you would see this spot right there. Moon phase. Lunar eclipse would happen at a full moon phase. This happens when the moon is between the Earth and the sun. Literally looks like a bite is being taken out of it. And that would cast a shadow of the moon upon the Earth, and it would look like this. So it is much more difficult to have conditions favorable for a solar eclipse than it is for a lunar eclipse because you have such a size difference between the moon and the sun. And solar eclipses are pretty amazing because we are the only place in the solar system, the only place that we've ever seen that has conditions favorable for a solar eclipse. A lot of places have eclipses, but we're the only place that has a full, complete, total solar eclipse. So it's a consequence of us having the moon, which is 1/400th of the size of the sun. You don't need to know this, but this is just kind of a crazy tidbitted fact. And the distance from the moon to the Earth is 1/400th of the distance between the moon and the sun. So because of those perfect triangles, those perfect ratios, that's why we see solar eclipses. But when the moon begins to venture outside, when it gets into these further out positions, because remember we're losing the moon at a pretty constant rate, then it will no longer be favorable for eclipses. Solar eclipse geometry right here. So you would only experience the total eclipse if you are perfectly within the umbral shadow, and only about 2% of Earth sees that, whereas 50% of Earth can experience a lunar eclipse. Only about 2% of Earth can experience a total solar eclipse. That is why it is on my bucket list. So if we look at this guy down here, you would only experience totality, is what it is called, when you're perfectly within the umbral shadow. If you were at this point right here, only that point would experience complete totality. And just so we see these eclipses because the sun and the moon appear to be the same size in the sky. So just a tiny review here. During the last unit, we talked about angular diameter very briefly and how we measure that. So if we take 1 degree, that is equivalent to 60 minutes, which is, remember, in every minute, you have 60 seconds. So we can break that up. So the angular diameter of the moon in the sky is about a half a degree, which is 30 minutes. So the sun appears exactly the same size in the sky. So when we begin to lose the moon, that will no longer be. And in ancient times, when the moon was closer, we didn't have that either. So the moon would have actually appeared larger in the sky during ancient times when the moon was closer. So looking at our eclipses again, when the moon passes in front of the sun, it can completely block the sun out. So again, since this happens during new moon, you would experience a solar eclipse in the middle of the day. So if you happen to be within this umbral shadow right here, you would experience complete darkness, would completely block out the sun. So here you can see, this is pretty amazing, this is taken from the space station, and you can see the shadow, this is a time lapse, of the moon passing across the Earth. So only this region is in complete totality, and you can actually see a bit of the penumbra surrounding that. So it would actually leave a path. And the cycle of eclipses, it actually follows these elliptical bands that go down the Earth. So right now, the last solar eclipse was total right about up here in the northern hemisphere, so the next one will move south. So they follow about 18-year cycles. So total eclipses are important because this is the only time when we can see the solar corona. The solar corona extends thousands and thousands of kilometers past the sun, and we can only experience that, or we can only see that. This is also what makes looking at solar eclipses so dangerous. We can only see this during a solar eclipse, so during complete totality. So this tells us a lot about the processes going on inside the sun, because we can take spectral measurements that are not possible except in a solar eclipse. So solar observatories actually simulate solar eclipses by blocking out the sun to be able to see these outer layers. So the corona and the chromosphere are the hottest layers of the sun. So when scientists want to look at the sun, they just simulate an eclipse. That's exactly what they do. And here again is that shadow of Earth, or shadow of the moon upon. So this will be your last slide, and I apologize, it kind of skewed some of my writing, but here obviously that's Earth. I don't know why it takes up 2 lines. It just does when I upload to this app. It functifies some of my writing. Here obviously is the sun. So here is a chart showing each of those different distances. So it is helion. We use helion instead of perigee when we're orbiting the sun. But when we're talking about something orbiting anything other than the sun, such as the moon orbiting us, we use apogee and perigee. So looking at that again, here would be the position that would be perigee, so the position closest to the gravitational body, to the primary body, and apogee would be furthest away. So then same sort of concept, perihelion would be closest. So in the Earth-Sun system, the sun is the primary body, Earth is the secondary body, so perihelion would be in this location, and aphelion would be in this location. And we'll see in the next unit that that actually changes the orbital velocity of the secondary body as it orbits around. So I highly suggest that you duplicate this picture in your notes. And this is it. Make sure you have watched these notes by Friday when we do our eclipse lab. Have a wonderful day. See you in costume on Friday.